Hi, I'm Tyler Foltz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today, we are going to start on the first part of the heavily requested Man Who Tried to Fake an Element documentary. Now, this one is pretty long. I think the original video is well over an hour. So this is probably going to take multiple parts. Not sure how many yet, but let's go ahead and get started and see where this goes.
Enrico Fermi.
I've never heard of this story, by the way.
To ever win a Nobel Prize. Fermi is Italy's top physicist. At the age of just 24, he had been made a professor at the University of Rome, and thanks to his commanding presence, his researchers had nicknamed him the Pope. Unlike the Pope, though, he was broke. Italy's dominance in science had long fallen off since the days of Galileo. If they needed a piece of equipment, they built it from homemade scraps.
This video is by BobbyBroccoli, by the way.
They would sprint back and forth.
Never seen any of his stuff.
To avoid getting a lethal dose of whatever chemical concoction they had just made. You see, they were trying to do the unthinkable. They were trying to create a new element. The periodic table back in Fermi's time looked a little like this.
So we're missing a few, but no uranium, no plutonium, no nothing, huh?
What you're familiar with, but with a lot of pieces missing. You'll notice a few gaps in the middle regions, specifically elements like technetium, francium, astatine, and promethium. But the biggest missing piece is at the bottom. We're missing like a full row and a half. What you see here right now are all the chemical elements that humans have found in nature. Just sitting around in the atmosphere as gases, in the ground, in rocks, even a couple liquids. Many of them are stable. A good number of them are safe.
I love the way this is animated, by the way.
A decent portion, however, are not, and are in fact quite dangerous. Radioactive samples that are firing off millions of invisible electrons that can penetrate.
I know what he's getting at, but just one clarification on radioactive. Just because it isn't radioactive doesn't mean it's safe. There's a lot of things on this that can kill you that don't have to be radioactive. And there are some things that can kill you because they're radioactive.
Your bloodstream. Radium, discovered by Marie Curie, almost certainly killed her.
Yeah.
Her daughter, Irene, very likely died from exposure to polonium, the other element discovered by her mother. So maybe you understand now why Fermi didn't mind having to sprint up and down his lab if it meant extending his lifespan by a few years. So how does one go about creating a new element? Well, on paper, it's simple. You add or remove protons. Hydrogen has one proton.
Just protons, right?
2. Lithium, 3. And if you keep doing this, count all the way up the periodic table, you'd eventually get to the heaviest element in the known world up to that point. Element 92. You know it as uranium. Here's the other part of the picture. An element is determined entirely by its proton number, but the number of neutrons can vary. That neutron number makes certain elements more stable than others.
One interesting thing is a neutron's actually a little bigger than a proton. You can increase the element's atomic number. In fact, that's how beta minus decay usually works, because beta is an electron. Well, a neutron is basically a proton and an electron combined with a little bit of extra mass energy in there. And that's how it gives off that energy in the form of an electron when you undergo beta decay. And that neutron turns into a proton. So you lose mass, and then your atomic number goes up under beta minus decay. That was something that was like, whoa, when I first heard about it when I was a kid.
Carbon-12, with 6 protons and 6 neutrons, is extremely stable. It will stay in that form untouched for billions of years. Carbon-14, with 6 protons and 8 neutrons, is radioactive. It's got an energy imbalance that it wants to rectify. And at random, it will convert one of its extra neutrons into a proton and fire off a dangerous electron to account for that energy imbalance.
Dangerous is relative. Any sort of, little subatomic particle can be dangerous, or in the case of radiation, gammas can have no mass whatsoever and still be dangerous.
All this beta minus decay. And what you're left with is an element with 1 extra proton. That's 7, aka nitrogen. Look at that! Purely by having 1 too many neutrons, the carbon destabilized and transformed into an entirely different element. Fermi's idea was to go to the furthest edge of the periodic table, uranium, element 92, and fire neutrons at it to try and artificially induce beta decay. If it worked, you'd be upgrading element 92 into 93, and if you could do it twice in a row, possibly even 94. Here's a fun problem though. How do you even know if you've created a new element? After all, you don't know what it looks like or what its chemical properties are. In this case, Fermi and his team had to rule things out by verifying which elements they hadn't created. They compared the result with the chemistry of all known elements.
I love this presentation and animation style. It's just really cool.
And couldn't find a single match. Unstable elements often lead to something called an alpha decay chain. That's when a nucleus spits out 2 protons and 2 neutrons.
A helium nucleus.
To a leapfrog effect, where element 94 turns into element 92, then 90, 88, and so on.
And the reason why it's alpha decay is the way it is because this is relatively common. That configuration right there of 2 protons, 2 neutrons, or a helium nucleus is quite stable. So it's a nice, sizable chunk for a radioactive element to basically lose mass in a relatively stable way. Because this is an interesting balance between the strong nuclear force that binds things together, the battle between it and electromagnetism, because you have a bunch of positive charges, protons, right on top of each other, and the neutrons, they are neutral, hence the name. So, which is one of the reasons why you get much bigger in terms of element size. You're going to need a lot more neutrons to keep that thing stable, because those neutrons can act as a little bit of a buffer. Like this example here of this alpha particle, 2 protons and 2 neutrons, that's not too bad. But uranium with 92, at least uranium-238, and 146 neutrons. So you need that extra buffer, and then it gets so geometry becomes part of this as well as how this force stays balanced. And even then, it's not completely balanced because it's radioactive and will eventually decay. Though uranium-238 in particular has a very long half-life on the order of billions of years.
Until they reach a stable element, which is often lead. The other possibility was that they had succeeded. They had made...
Lead is an example of something that is not radioactive at all, but is poisonous. So, there you go.
Elements 93 and 94 for the very first time. The discovery catapulted Fermi into overnight fame. He was Italy's pride and joy, and obviously, he got first
I didn't know the
dibs
Pope
on
thing. That's
naming
kind of
those
cool.
2 elements. Although he was under a lot of pressure to name the element after a symbol of ancient Rome, fascism, from the word
Fascism.
fasces. Recently, however, the symbol had taken on an entirely new and terrifying meaning. It was the symbol of fascism.
Especially in that time period. Yep.
The name was none other than Benito Mussolini. Yeah. Fermi did not follow this suggestion. 4 years go by. It is November 10th, 1938. 2 things happen that day. In Germany, it's the Night of Broken Glass. In Italy, a wave of anti-Semitic laws are introduced. Fermi's wife Laura was Jewish, and her passport was on the edge of being revoked. So when the phone call came in that day at 6 p.m., that Enrico Fermi had won the Nobel Prize in Physics, their family didn't think twice. Fermi, his wife, and his children packed their bags and immediately traveled to Sweden. They did not return to Italy, and instead settled in the United States. And almost immediately after they arrived there, Fermi got the news. He had been wrong. He hadn't created elements 93 and 94. He had done something much crazier. He had made an atom explode. When Fermi declared that he had made new elements, he did so because the chemical properties didn't match up with anything as light as lead. Turns out, he should have looked even lighter. A group in Berlin had repeated his experiment, and they saw something really unexpected. They were seeing krypton and barium, 2 elements that were far too light to be the result of an alpha decay chain.
Note that you're not guaranteed to get krypton and barium when you split uranium. You can get anywhere between like atomic mass of like 80 through 100 for the little one, and like 120 through 140 or something like that. That's where you can get a whole bunch of other stuff, but that's where the probability peaks are. And it's just a big probability numbers game of what you're actually going to get when you split uranium. You can also get mostly around 2 neutrons that are free, but sometimes you can get a third or even 4. So it's just a big Monte Carlo situation is what all of nuclear physics is, really. Just going to Vegas.
But if you add up their proton numbers, 36 and 56, you get 92.
So no free protons in that was good to know. That's so unlikely.
That releases an absurd amount of energy. In reality, Fermi had discovered nuclear fission, a discovery that would go on to fundamentally reshape the upcoming war that he had just fled from, a discovery that would go on to dictate a global power struggle that would last for half a century. Entirely by accident, Fermi had falsely claimed.
So he's going to go through like decades of this stuff. Wow.
Half a century later, one man would make a similar.
You can see why this is over an hour now.
Entirely on purpose. This is a story about Viktor Ninov and the race for the periodic table. I gotta show you something. This is the periodic table. I'm betting you recognize it, but it doesn't show the whole picture. Each element has a unique number of protons, but each element can have any number of neutrons. We call these nuclides. Some are more stable.
I've always heard it as nuclides. No E. I don't know if that's a regional thing, but I distinctly, getting the book, the chart of the nuclides, which tells you what decays into what, how it decays, what's the energy from all that, had something like that on me almost all the time through college. And it was this big reference material. We'd use it on tests and stuff like that all the time. I think the reason why they gave it to us, it was easier then the professor, whoever, to remember what each parameter is on each decay chain. And you couldn't memorize it. It was much too big to memorize it. I mean, some people might have, but they might be the same sort of people that memorize 1,000 digits of pi or something like that. But I've never seen it spelled nuclides.
This is hydrogen, exactly 1 proton. This is helium, 2 protons, 2 neutrons. Every possible proton-neutron
but there's also helium-3
that's ever been observed is present on this chart. Every time we go up a row, that's a new element. I don't think my audience has a lot of overlap with football fans, but if it does, for some weird reason, think of this as scorigami, but for chemistry.
I don't know what scorigami is, so.
That didn't exist before, and maybe never will again. See, inside a nucleus is a pair of competing forces. On the one hand, you have the strong nuclear force. At
that's what I was talking about earlier.
ranges, it is able to glue together protons and neutrons into bundles. But on the other hand, you have the repulsive electromagnetic force. Protons all have a positive charge.
The key thing about strong nuclear is it is absurdly short range, so it doesn't even affect the electron, for instance, at the end. That's way too far away, so in close range around the nucleus, which is probably why it's called a strong nuclear force.
Want to push each other apart. Only when the strong nuclear force can overcome the electromagnetic force can you have a stable nuclei. The neutrons, which are electrically neutral, serve as a kind of packing material because they don't repel each other.
I like
they can
that.
Act as a buffer
it's a good term
for protons, making a nuclei more stable. Notably, the same element can have different numbers of neutrons, with some being very stable and some decaying immediately. We can actually see those stable nuclei quite clearly. They are the tall pillars in brown. The height on this chart represents the half-life of a given nuclei.
That's what I thought.
Half-life is the time it takes for a sample to be reduced by 50%. The taller it is, the more stable it is.
This chart doesn't appear to be to scale, even a logarithmic scale. I mean, it is in terms of element, but in terms of the height, the third dimension of it jutting out at you, because those blue ones, some of those are milliseconds, nanoseconds, absurdly short amount of time. What's this, like a nitrogen with 30 neutrons on it or something? Ain't going to be around for long, if at all.
The thing you can see is that for the lightest elements, the most stable combinations are those where the proton number equals the neutron number. See this line? Perfectly balanced. You can trace this line from hydrogen up until about calcium, and then the trend starts to diverge. For most elements, it's actually more stable to have more neutrons than you have protons. If we follow the path all the way up,
that positive charge gets pretty big.
This is the path of stability. As soon as you stray even a little bit from that path, you plunge into the realm of radioactivity. The red pillars here are essentially stable, with half-lives in the billions of years.
Yes.
But by the time you make it to the oranges, you have a half-life in the minutes. A couple hours go by and a sample could be reduced to nothing. And if you touch the water, in blue, those half-lives are in the seconds. And the deep blue, well, that's milliseconds. Or in the worst cases, the half-life is so short we can't even measure it.
I love this infographic.
Nuclei, there's a good chance there's only ever been one of them in existence in the entire universe.
This needs to be shown, and for all I know, it is, because I'm looking at 15 plus years ago of when I started undergraduate school. Yes, I'm that old. But this is way more interesting and easy to understand than here's a book of the chart of the nuclides and have fun. No, this is super, super cool.
Nuclei is so unstable it could never occur on its own, but we forced it to. The beauty of this chart to me is that it's almost like a topological map of our journey through the periodic table, like a mountainous peninsula surrounded by a raging sea of radioactivity. The sea even has tides. Way up here in this chasm, you'll often get swept away in an alpha decay chain. That's when an element spits out 2 protons and 2 neutrons. It moves 2 spaces diagonally downwards, like this. A cascade that doesn't stop until you reach a stable element. On the south side of the mountain pass, there's a different type of tide. Fermi's beta minus decay. You lose a neutron, but gain a proton, like this. If you're smart, you can use this to go up a step, potentially creating a new element. But on the other hand, to the northern side of the mountain pass, there's beta plus decay. You lose a proton, but gain a neutron.
So that one, the plus, that is a positron, which is antimatter. It's the opposite of an electron. And a positron and an electron will annihilate each other, and then you get 100% of the E equals mc squared of both particle and antiparticle. That can happen through through pair production. It can happen through beta plus decay. But positrons, you're not going to see them in an atom, in an electron orbital. That's not a thing. But yes, a type of radioactive decay can create antimatter, which is pretty cool.
No matter where you are, however, every part of this sea is fighting you. The tides of radiation always lead you back to the same place. No matter where you started, eventually you get pushed back to shore.
I haven't heard beta positive in a while. That's cool.
Of stable nuclei. Some people refuse to accept this. They push back, trying to explore more of the sea and potentially uncover more and more land.
I like it. The land-sea explorer analogy is really cool.
Made it as far as the uranium chasm. Over the course of the next 50 years, several different labs would make the same pilgrimage up this mountain, and every new pilgrimage would fill out more and more of this chart. The protagonist of our story, the intrepid Viktor Ninov, claimed he had made it up to here. It's pretty far, huh? To meet him, we've got a bit of a journey ahead of us.
The scale?
And we're gonna
element 150?
To cross this sea, we're going to need a captain. Fermi would go on to do important things. His most well-known achievement is building the first nuclear reactor under the stands of a Chicago football field. But he stopped.
That's its own crazy story right there.
That chase would be taken up by an entirely different team. The discovery of the real element 93 was weirdly unceremonial. On the west coast of America at the University of California, Berkeley, American physics was in full go big or go home mode. Berkeley at the time was home to the world's biggest cyclotron, the best tool in the biz for element hunting. A cyclotron is a type of particle accelerator. It uses magnets to rapidly spin charged particles around in circles and then smashes them into targets. Now, this isn't one of the multi-mile rings that you're probably thinking of. Those are actually too powerful for making new elements. For this, you need something a bit more delicate. Berkeley's state-of-the-art
I don't think those existed back then either.
In diameter, and it could pelt a uranium target with neutrons, again hoping for Fermi's predicted beta decay. And one day, after finding a radioactive lump that matched no known samples, element 93 had officially been confirmed.
Nice.
We now know it as Neptunium. The credit for this discovery went to Edwin McMillan and Phil Abelson, but the celebration was short-lived. Their publication was met with silence from the academic community. no one dared acknowledge the breakthrough lest it give the Germans any inspiration. Although America hadn't yet joined World War II, they were preparing to, and so Macmillan and the rest of the lab's top scientists were soon drafted into the war effort, working on radar, or in some cases, the Manhattan Project. That left a vacant seat to take over the element hunt. That's where our captain comes in, Glenn Seaborg. As a descendant of Swedish immigrants, they had left their home country with the last name Sjöberg. Upon reaching Ellis Island,
I never knew that about Seaborg.
Decided that their new name would actually be Seaborg, and it stayed that way. This customs officer had no idea that his half-assed spelling attempt would one day make it on to the periodic table.
That reminds me of that Solo movie with where Han didn't know his last name, so some random Imperial officer says Solo because you're your own man.
From a young age,
I wonder
if
that's what that was based on. If they looked at Seaborg.
From icy Michigan to sunny California, an 11-year-old Glenn decided to add an extra N to his name because it looked cool. Can't argue with that, Glenn. And on another day, as a 24-year-old chemistry student strolling through the Berkeley campus, someone from the radiation lab stopped him and asked if he could help them separate out some chemical samples. He was just the first chemist they found on campus. Seaborg would eventually work his way up through the lab, and with Edwin Macmillan gone, he asked if he could take over as the new captain of the element hunt. Although Macmillan never got to try it out, he had come up with a recipe for element 94, and good old Glenn was going to get the first crack at it. If you add one neutron to uranium, it beta decays into element 93. But say you fired a proton and a neutron. The proton would immediately bump it up into element 93, and then the extra neutron would have a chance at beta decaying, upping it one more time to element 94. It really is like an absurdly delicate game of Jenga.
One interesting thing, now this isn't 100% accurate, but to tell like what isotopes of, say, uranium or plutonium are fissile versus fissionable. Fissile means it'll easily fission, you just throw a thermal neutron at it. And fissionable means you need a fast neutron, which are extremely rare to get from fission. There are types of reactors designed to operate with fast neutrons, though. If it's an odd number, like uranium-235, it's fissile. If it's an even number, like uranium-238, it's fissionable. Again, doesn't work in 100% of all cases, but just as a quick memory trick, you'll probably be right about 80% of the time.
So yeah, that's how you make plutonium. It's safe to say that the discovery of plutonium was kind of a big deal. It's actually an even better fuel for a bomb than uranium, which was the original plan for the Manhattan Project. And thus Seaborg and his team were immediately drafted to Chicago to work with, oh, hey, it's our old pal Fermi. There they spent months artificially making enough plutonium to flatten a city or two.
Now plutonium is a lot, you don't need nearly as much of it. It's a lot more reactive than uranium. So that's why the second bomb, the Fat Man bomb, used plutonium. Little Boy used uranium, and Little Boy wasn't as powerful, was less efficient. Now part of that was the geometry of the design. And also, it required a lot more work to enrich that uranium. I think they ended up using all the enriched uranium in the world at that time period to make that, because it was such a new concept. But plutonium, they were able to test that one. They didn't want to test the uranium one. One, they'd use up all their resources, and two, they were more confident that it would work with the math. And it's such a simple device to use that it was easy for them to go ahead and just have your first test be an actual nuclear attack. The plutonium one was a bit more complicated since it was an implosion type device. It had to come in a spherical shape of how the explosives moved the radioactive material together, the fission source, the plutonium. And then it ended up just creating an even more powerful nuclear bomb. That's the one they tested in the Oppenheimer movie.
It was difficult and hazardous work, and at one point a lead brick fell and broke a beaker, and 25% of the world's entire plutonium supply was soaked into a copy of the Chicago Times.
There wasn't very much.
The Manhattan Project is a story that's been told many times by people better equipped to tell it than me. The story we care about involves Glenn Seaborg and Berkeley. By this point, they have enough plutonium for their bomb, so Glenn and his team are free to ponder some other questions. Why stop at 94? Surely the periodic table didn't end at such a weird number. And they didn't even have to reinvent the wheel. Instead of starting with uranium, just start with plutonium and fire neutrons at that. To go back to the Jenga analogy, you're trying to build a taller tower, but the bottom rows are radioactive, and they keep disappearing on you. But as long as you're building the tower faster than it's disappearing, maybe you can find a new element.
So there is something as far as it falling down like that. You can have, it's not really decay in the sense of it. You can have a spontaneous fission, which just think of it as a really big alpha decay, because you happen to just throw so many neutrons at this particular isotope that some isotopes, this is pretty rare by the way, because usually alpha's a more thing, would just spontaneously fission, and that's when a bigger chunk breaks off because it's that much more unstable. Which, kind of using the Jenga analogy, that's when you knock half the thing off rather than just a small piece. I was never any good at that game.
At this point, we're going to pick up the pace a bit. There are still a lot of missing pieces between us and our friend Victor Ninov. If you want to read more, I highly recommend the book Super Heavy by Kit Chapman. Essentially though, the timeline went something like this. Element 93, discovered by Berkeley. Element 94, Berkeley. Element 96, discovered by Berkeley members in Chicago. Element 95, Berkeley members in Chicago. 2 atomic bombs are then dropped on Hiroshima and Nagasaki, killing upwards of 250,000 in the immediate blast and poisoning the ground and air for decades after.
Decades after, now I know he didn't, this video's not on nuclear weapons or the Manhattan Project necessarily, so he might not have done as much digging in this, but they were airburst detonations, so a lot of the fallout just blew away. A lot more people died from the blast effects of the nuclear bomb than the radiation. Now, radiation did kill some people, and that is a horrific way to die. I've talked more about this in other videos, but if it would have been a surface detonation, that would have been a different story. Then there would have been more damage. Then there would have been a higher percentage than what was due to radiation and contamination, because it would have caused so much contamination onto the ground. Also, it would have done less damage in terms of the blast because it was closer to the ground, not as much room for that expansive force of the explosion to damage structures and kill people.
Next up was element 97, once again found by Berkeley, and since they definitely earned it at this point, they named it berkelium. Element 98, hey, guess what? It's Berkeley again. They named it californium this time. With 4 elements in a row, the New York Times joked that they should have just gone with universitium, uvium, californium, berkelium.
That would have been awesome.
At this point that the Nobel Academy
I like
finally
uvium.
acknowledged Berkeley's achievements, and so Edwin McMillan and Glenn Seaborg shared the Nobel Prize in chemistry. Next up was elements 99 and 100, and this is going to sound extremely stupid. I swear I'm not making this up. America dropped a nuclear bomb in the middle of the Pacific Ocean, sent fighter jets through the very, very top of the mushroom cloud to collect samples, raced like hell to get the rapidly decaying lumps back to Los Alamos in New Mexico, where they were then analyzed to see if they had made any new elements.
Is that why they did that nuclear test? Or maybe they did a couple of things. It's like, hey, since we know you're setting off a nuke here anyway, we're going to go ahead and take a little bit of a sample in a jet. Fighter jets in general were fairly new at the time.
Yes, and unbelievably,
never heard of that one.
Since Berkeley helped out with the analysis, they were co-credited with the discoveries of 99 and 100. These were named after 2 of the field's greatest minds, Einstein and Fermi.
So on the note of probability, there's a chance that with all those neutrons in a fission reaction, that yeah, you can end up with weird results like this. You get some super heavy stuff as a result of fissions, few spontaneous beta decays, kicking you up the periodic table, and you end up with just some really weird stuff like this existing at some point in time. For these things probably have super low half-lives. I don't know them off the top of my head, but yeah, that's you can get some weird results because the number of atoms of plutonium in a bomb are a lot. You're talking on the order of several kilograms of the active stuff. Multiply that, just the simple thing you learned in high school chemistry of get your molar mass, multiply it by kilogram, and Avogadro's constant, then you're going to end up with on the order of 10 to the 23rd power plus atoms and that many reactions. So even weird things that are 1 in a trillion chances of happening or less, you just played the game 10 to the 23rd time, so you're going to get some pretty weird stuff every now and then. It's fascinating.
Both of them had passed away just months earlier. And soon enough, there was element 101, again found at Berkeley, named to honor the creator of the modern periodic table. It truly was one of the most dominant streaks in scientific history. Every other lab was left playing catch-up and could do nothing but watch as Berkeley added nearly half a row to the periodic table.
This is a fascinating documentary. I think we're going to go ahead and take a break there, but join me again soon for part 2. This is really fascinating. Thanks again for the recommendation. I love the presentation style of it kind of panning over, and looks like we still have quite a bit of ways to go. So this will be another fun little video to react to. Thank you very much for watching. I'll see you next time.